windows on the right-hand side too, right? I'm gonna close it down. Okay. All right, so let me know if you guys can't hear me or if I'm talking too small. But anyway, so my name is Zhang, and I'm here to talk to you about simulation of Martian penitentes. And so my supervisor is John Morse. And well, let's get started. So introductions, what are penitentes? So penitentes are blade-like structures, as you can see here, and they are formed by sublimation. And so on Earth,
I think it's frozen.
it's
Sorry.
it's frozen. Like you can't see the slides being changed.
It's good now.
All right. Okay. So I'll not make it full screen, and you guys can just look at the sidebars. Oh, anyway. So where was I? Okay. Penitentes are blade-like structures that are formed by sublimations, and so terrestrially they have strong uniformity in spacing. So these are generally a few meters apart, and they also have a strong uniformity in orientation as well. And so they will tend to orientate east-west. And so where can you find penitentes? On Earth, they're usually found in the mid-latitudes, especially in mountainous regions. So that's the Andes, the Alps, and the Himalayas. And the Andes is where you can find the pictures of penitentes on the previous slides. Outside of Earth, penitentes have been found on Pluto, and they're methane ice. And they're also suspected of forming on Europa as well. And so what I do is I want to see if whether it's possible to form penitentes under the Martian conditions. And I'm going to try and see what their properties are should their formation be possible. And so let's talk about how penitentes are formed in the first place. So they're formed from differential heating of an icy surface. So as you can see here, you have incoming sunlight coming from the top, and it bounces off of the ice surface of penitentes, and the light will bounce to the bottom of the structure. And so what you have is you have uneven heating, where there's more heating at the bottom and there at the sides. And so that causes the ice at the bottom to sublimate more so than the walls, and that's how penitentes are formed, and that's how their structure is maintained. And so first, to do this under Martian conditions, we need to see how incoming solar flux behave under the Martian sky. And so on this left plot here, you can see is a typical day at latitude 40, at solar longitude 100, and this is what the sun path is like throughout the day. And so now what we need to find out is how does that light scatter under the Martian sky? And so what we do is we use a radial transfer model, and we take data from the Mars global climate data, and then we average that over 7 Martian years. And so we feed the incoming sunlight through the model, and then we will see how it is scattered, as you can see here through the right plot. And now, next thing we need to know is how does the surface absorbs the light? And so on this plot here, it shows you the incoming sunlight and how much energy is absorbed by the surface. And this line right here is defined as the bottom third depth. So if there's more heat absorbed by the surface below this line, then we define that as penitentes are favored to form. And that includes incoming sunlight and the reflection, even though this plot doesn't show the reflections. And then what we do is we test out different orientations. So this is east-west oriented penitentes. So we rotate that, and then we figure out at what orientation do you get most heat going to the bottom as opposed to the sides. And so we do this for every latitude and for every solar longitude. Now, as for the actual growth rate of the penitentes, so Claudine and al. Actually analytically solved this, that for a given spacing of a penitente, the growth rate is determined by the heat conduction of the ice surface, so how heat is distributed along the icy surface, and just as importantly, how vapor is distributed above the surface. And that's important because it controls the saturation of the vapor above it, and so that can actually impede sublimation. And so since Claudin analytically solved this for each wavelength, what we do is we test every single wavelength, so from millimeter size to tens of kilometer size, and then we will find which wavelength has the fastest growth rate. All right, so first results, I want to introduce something called the differential heating factor. And so that is the ratio between the heat absorbed at the bottom divided by the heat absorbed at the sides. So differential heating factor above 1 means that penitentes can form. And so first we're going to look at the clear sky regime. And this shows you the solar longitude and the latitude up here. So this is the North Pole, the bottom is the South Pole. And this is a contour plot of the differential heating factor, and anywhere that's colored is when penitentes can form. And as you can see here, penitentes cannot form above 60 degrees on either hemisphere. So that's pretty consistent with Earth. And on the right plot, the color map also shows the differential heating factor, but the red lines here shows you the preferred orientation. And under the region where penitentes can form, you can see that they will orientate east-west. So this is pretty much the same as Earth, and it's not surprising considering that Mars and Earth has very similar obliquity. And then we introduce dust scattering, and this is where things get interesting. And you can see that because of dust scattering, you can actually get penitente formation all the way up to the poles, more so in the South Pole than in the North. And you look at the plot on the right here, this shows the preferred orientation again. So when you're underneath the sun, the preferred orientation is pretty much east-west. But at the polar regions, you can see that they orientate north-south. And so now when you do this on a 30-degree inclination, this shows that you can pretty much form penitentes anywhere at any time. And except for the fact that for 30 degrees though, at the poles, you still get north-south preferred orientation. But if you crank up to a 40 or 50 degree slope, you would expect east-west orientation with the concave pointing towards the sun. And so let's look at the preferred spacing. So here you can see our test wavelength size from meters to tens of kilometers. And the fastest growth rate occurs at 25 meters. And so for penitente with a wavelength of 25 meters or a spacing of 25 meters, a meter deep penitente will deepen at only 0.6 millimeters under the northern polar conditions. And we use the northern polar conditions because it's the most likely spot for us to host penitentes. And so what this means is that for observable penitentes to form, you kind of need a year-round favorable penitente formation. And so this is what this plot shows. So this plot shows the cumulative differential heating factor, the heating factor over the Martian years. And above 1, penitentes can form, below 1, they cannot. And you can see that for the North Pole, penitentes does not form year-round, but on the South Pole, it can. And the orientation at the South Pole, that's these red lines here, is north-south. However, when you have a sloped surface of 30 plus degrees, penitentes can form not just on the North Polar cap, but pretty much anywhere. And so an important factor is the scattering effect. And here I got you the contour plot of the scattering case, and this shows where penitentes can form. And below here is the optical depth that's taken from the Mars Global climate database, averaged over 7 years at a sample wavelength of 880 nanometers. And I got to thank Christina Smith for providing me with this plot. And so, you can actually see the effect of scattering over here. So if you look at this plot, this block or this region of high activity, this corresponds to this part right here. And so this is the differential heating factor. And so what this means is that when you're underneath the sun, and there's a lot of scattering going on, the light will actually tend to bounce more to the walls than to the bottom. And so it impedes penitente growth. But if you look at the scattering at the polar regions around here and here, and that corresponds to here. And so when the sun is at low elevation, the scattering effect actually causes some of the light to reach down into the bottom of the trough, and thus penitente formation is possible at the poles. And so that's why the South Pole is actually more favored to form penitentes than the North. And so conclusions, dust scattering allows for penitentes on a flat terrain to form at high latitudes. The poles, penitentes should have a north-south orientation. The preferred spacing of penitentes, water base, is about 25 meters, and they will deepen about less than a millimeter a year. And so insulation and dust activities at South Pole favor penitente formation more so than the North. But if you have a slope terrain of any kind, that will definitely help the formation of penitentes. And I think that's about 12 minutes, and I'm pretty much done. So are there any questions?
Oh, we have a couple of questions here at McGill. So I guess what I'm curious is what do you learn if you see or don't see penitentes on Mars? Like there must be some other parameters like wind or something.
Oh, yeah. There's wind, and yeah, I guess I kind of spat that over. Anyway, so this goes back to why penitentes on Earth are only found in the mid-latitudes and highlands. So the mid-latitude is because the sun is overhead, so you can create penitentes. But and at the highlands, you actually have low wind conditions. So vapor sort of just diffuses in ambient wind. So that's how the spacing is sort of determined. If you include wind factors, I think it will change the spacing, but not so much the orientation.
Okay, so in principle, you could learn something about the winds on Mars by studying these penitentes.
Yep, so for penitentes of any given wavelength, you can kind of infer how much wind is present. And so for 25 meters length, you would assume that there's no wind.
Another question for Bill Bernard. So if you have high definition imaging, or if you image on the surface of Mars and you see a field of penitentes, can you then back out sort of an average tau, an average dust content of the atmosphere, or what parameters can you constrain better by the actual observational spacing or depth of penitentes?
Well, the depth is kind of harder to realize. So you're asking if you can find the spacing and the depth. What atmospheric conditions can we infer from that?
Sure.
Yeah, well, if it's at the polar regions, then we know that there's a lot of dust activity. But the thing is that since it's expected for these things to take years and years to form, so which would mean is that if you have any polar region where there's penitentes, observable penitentes, you can assume that, you know, there's a lot of scattering happening around this area year round and year after year. So I think that's something you can draw from that.
And then just one more question.
Mhm.
As you change the seasons every 2 years on Mars, 2 Earth years on Mars, you're shifting material from one pole to another. How does that influence?
Oh, can you repeat the question? There's like a banging noise in the background.
So an entire Martian year,
Mm-hmm.
shift material, mostly CO2, I guess, from the North Pole to the South and back again. How would that changing of pole density or volume of ice influence the morphology of the penitentes?
Oh, so what I've worked on so far is actually with water-based penitentes, and so you're asking for CO2, but CO2 penitentes is possible under Mars. I haven't done the math myself, except I don't think it should change the morphology, because you know, the CO2 is just going to deposit, and then when light hit it, it's just going to sublimate a certain way so that the wavy structure is maintained. But I don't know how the morphology of penitente is affected by that.
Okay, thanks.
No problem. Is there any other questions? I think I'm done.
Okay, Brittany, do you want to start now?
Or I'll get off now.
Just 1 second. We're trying to deal with the potential echo in the room. I'm just checking to see if there's an echo, if that sounds okay. All right. All right, everyone can hear me? Okay. All right, so I'm also a master's student at York. Well, actually Zhang was not a master's student, but I'm also a student at York, and my supervisor is John Morris, and I'll be talking today about my work to constrain the phase function and ice crystal geometries of Martian water ice clouds. There is a slight echo over here. Not sure if we can do anything about that. That's okay. I'll just go ahead. All right. Okay, so I will begin with an overview of Martian water ice clouds and the phase function and why we care about them, and then talk about our work to constrain those parameters from both surface using MSL and orbit using MARCI. And then I will just simply go over the conclusions at the end. Right. So a lot of those outside of the planetary community are not necessarily aware or surprised to find that Mars has water ice clouds. And those within the planetary community didn't really understand or appreciate the impact of them until about the 1990s, when we learned about the annually repeating feature called the aphelion cloud belt. And this is a feature that occurs as a result of Mars's orbital eccentricity. When Mars is furthest away from the sun during aphelion, the atmosphere globally is colder and allows for clouds to condense more easily and freely, especially around the equator, between latitudes of -10 and +30 over the same kind of extension of solar longitude. And solar longitude is just a measure of the planet's position in orbit, with 0 degrees being the vernal equinox of the northern hemisphere. Sorry, we're still having a bit of an echo in here. Do anything about it. That's okay, we'll just leave it. All right, so the ACV is typically repeated from L sub s of 60 to about 180 every year. And as you can see in the CMIS plot of water ice optical depth, you can see it from around that same region in the same latitudes year to year. So if you're interested in studying the clouds, this is a good time to do it because they're very frequent and they're very opaque during that time. So what we're interested in looking at in this work is the phase function. And it is a dimensionless parameter, so it has no units, and it describes the angular distribution of scattered radiation from a scatterer, and it's dependent upon the scattering angle. And so in the case of clouds, the scatterers are not a sort of uniform cloud, but rather each individual ice crystal that makes up the cloud. And the scattering angle is simply equal to pi minus the phase angle, where the phase angle is the angle between the light source, the scatterer, and the observer. And so the bottom plot I have here is the phase function versus scattering angle for 7 different models. And this is from Yang and Liu 1996 and Yang et al. 2010. And so you can see that along this entire scattering angle range, there's almost like a fingerprint or a spectra for each. So in theory, if you can constrain the phase function of the clouds you're observing, then you can constrain the dominant geometries of the ice crystals in the clouds that you looked at. And another really cool thing with the phase function is that you see certain peaks at different scattering angles. And these correspond to different optical phenomena that we see here quite commonly on Earth, like the 22-degree halo and 44-degree halo parhelia arcs. All of these are caused by different geometries and orientations, and there's something that we've not yet seen on Mars. So that tells us that maybe something else is going on. Maybe there's another dominant geometry in the clouds on Mars, and it's worth investigating. So that leads me to the goal of my work in my master's, which is to constrain the phase function as well as the ice crystal shapes and geometries of Martian water ice clouds, both from the surface using MSL and from orbit using MARCI. And so we'll start with the work from surface using MSL. Because I've been a part of the mission, I was able to work along with the engineering team under the guidance of my supervisor to propose this observation called the Phase Function Sky Survey. And it ran on the NavCam imagers of Curiosity once a week during the ACV season of the last Mars year. The goal of this observation was to capture as much of the sky as possible at a single time to try and determine the phase function over as wide a scattering angle range as possible. So this observation consisted of 9 different image pointings with 3 images taken at each pointing. And so what you can see here is an example of one of the frames for each pointing in this observation. And you can see that we do try to capture as much of the sky as possible. And so we ran this 35 times and got a lot of data from it. And on the right, you can see our results where the red dashed line is our derived mean phase function, and it's compared with those 7 different models that I showed you previously. We were able to do it over a range of 18 to 153 degrees in scattering angle. And then we did a goodness of fit test with a chi-square analysis and p-test to see which of the models best agreed with our derived phase function. And we found that aggregates had the best fit, and then plates and columns and bullet rosettes had slightly less, but still good fit. And then droxels and spheres, which are these blue curves, had the worst fit. And so what's interesting with those results is that with the plates and columns, you expect to see those peaks around 22 and 44 degrees. So you would expect to see halos on Mars with a good fit of those. But yet we still don't see that. So that leads us to kind of think about what else we're missing, whether there's additional scattering from dust in the atmosphere that's affecting it, sublimation of ice crystals. Is there a bias in the types of ice crystals that we're observing with shapes at different layers, and whether we're looking from surface or from orbit? So we were able to publish these results in Planetary and Space Science in January, which was very exciting. And that was it for that. So now to looking down from orbit with MARSI, or the Mars Color Imager. The great thing working with orbital data is that we have a much larger spatial extent to look over. So as opposed to looking from up from Gale Crater, where we're just looking at sort of a microclimate, we can get a larger range of samples over the globe. And we're working with publicly available data from the primary science phase of MRO's mission. And so we downloaded it, and then I produced an algorithm to calibrate the data, to add in assumptions to isolate pixels most likely to contain clouds. And then we used the SPICE information kernel data system to determine the illumination angles and latitude and longitude corresponding to each data point. And we also worked with someone at Harvard who catalogs dust events and overlapped our data with their data to try and minimize contamination from dust in our work. So this plot on the left shows you phase function values over our entire observing time. So this is 2 Mars years, and we have latitude versus LS. And then these black and red dots correspond to catalog dust storms, and the red ones are dust storms where clouds were observed. So we filtered out all our data that overlapped with that as a result. And then we determined the phase function for each of those 5 filters. This work is still ongoing, but we're looking at sort of seasonal and geographic analyses, looking at the distribution of our data points, trying to look for surface influences in different filters, and looking how the phase function changes with season. But initial results show that we do agree with what we saw with MSL in terms of aggregates being the best fit. And also our derived phase function from MSL does agree quite well with what we look at in the blue filter for different seasons. We also did a little bit of work with MARSI data and produced this sort of little mini project, a research note. The one scattering feature that you can see on Mars quite frequently is the opposition surge. And when you're working with a push broom imager, it gets kind of smeared out to look like a long strip. But when you add certain filters of MARSI data together, you notice that the opposition surge peaks at different latitudes in different filters. And so when you produce a composite image, it almost looks like a rainbow. And so we wanted to look at what was going on there and kind of prove that this isn't an actual rainbow. And we found that, in fact, when you look at the scattering angles observed by the different filters, which are permanently placed on the CCD of the imager versus latitude, we see that each filter has a different field of view at a different point in orbit, and so sees the 180-degree peak at a different point, and that's what it's a result of. So I will just leave you with my conclusions here, which are to say that, and summarize, that we found that aggregates do seem to be the best fit, but we do expect to see a combination of many types of geometries dominating the clouds on Mars. And we see a similarity in what we observe from the surface and orbit, but there is a bit of a difference as well. Because a lot of the smaller ice crystals are at the top of the clouds, we do see a higher signal for those looking from orbit. And we also do see lots of clouds formed around orographic features, which is cool as well. So I'll just leave you with this, and I'll be happy to answer any questions.
Hey, this is Nick again at McGill. So I guess I have 2 questions. The first one is, if you had a Lambertian scatterer, would that just be a flat phase, like scattering phase function? Is that right?
Yes, correct.
So basically the Martian water clouds are best good approximation Lambertian reflectors, unlike the more interesting phase functions for Earth clouds.
Sorry, I was just trying to go back to this plot here. Sorry, could you repeat the last part of that?
Oh, well, I mean, it looks like your data, if you go to the next couple slides later than this, where you show your actual results, it looks like the results are relatively flat. So unlike all those interesting shapes that lead to troughs in the scattering function, it looks like real Martian water clouds are actually sort of close to Lambertian, which I guess sort of makes sense because aggregates I would assume would be the closest to Lambertian as well. So what does this tell you about how these clouds form on Mars? Like presumably they must be forming in some fundamentally different way from water ice clouds in Earth's atmosphere.
All right, sorry, I'm not muted now. So yeah, so definitely it is kind of sad that the plot is so flat, and I found with my results from Mars C2, it's a lot flatter than expected. So it is telling us that at least the ice crystals that are dominating our signal, which is aggregates, are scattering a lot more evenly. And that could be due to a bias that aggregates are typically a lot larger in radius. And so they could be dominating what we're seeing. And then the smaller ice crystals, which have sort of more pure shape before they are kind of clumped together, are not really getting through very much. So it is unfortunate, but it would explain why we haven't seen any of these fun and exciting scattering phenomena on Mars yet.
Cool, thanks.
If there are no other questions, I can ask one more. This is Bill at McGill. What do clouds nucleate on Mars compared to Earth? Dust particles, I presume. Does that affect morphology?
Yeah, it definitely does. So there's a lot of different dust particles for them to nucleate on, and that's a very good condensation nuclei. Also, it's been hypothesized that ice 1C, which is a form of water ice that has oxygen atoms in a cube, or sorry, not a cube, but rather in a square shape instead of hexagonal things that we typically see here on Earth. That could be a very strong nucleator for ice 1H, which is the hexagonal. So that could be affecting it because we see that a little bit here on Earth, but not so much. So that could potentially be affecting it as well.
Thank you.